not.
Welcome, everybody. So today we have the pleasure to have the second lecture on kernel methods by Arthur Gretton. And so Arthur, I leave you the stage.
Okay, so thank you and good morning, everyone. So yeah, today I'm going to do the second lecture. So yesterday we learned a lot about kernel methods and we understood how to construct infinite feature spaces. And in particular, we understood a reason for constructing these infinite feature spaces, which is to allow ourselves functions of these features which are smooth. So this was the key, I guess, take home from yesterday's lecture. So yesterday was a little bit abstract. Today, we're going to look at how we can use these tools for particular applications, and we're going to focus on comparing probability distributions. So remember this slide from last lecture. I have a set of objects from some distribution, here dogs from some distribution P. I have another set of objects from a second distribution Q. And my goal, based on these two sets of objects, is to tell whether P and Q are different or similar. Okay, so this, this slide is today's slide. This is what we're going to talk about today. All right. Now, the particular measure of difference between
Yep. I don't see the slides changing. Are you changing slides?
I am changing the slides. Am
I the only one in this situation?
No, it's the same here.
Yeah, it's the same front slide.
Okay, let me try this. Bring your shared window to the front. Sharing is paused. Let me see. So there is on Zoom, there's a thing saying bring your shared window to the front.
I think you have to make it full screen first and then share.
It is full screen. Yep. One moment. How about, can you see it now?
No.
It's the same. Oh,
okay.
Something's
changing. It is changing?
Now.
Okay. Now I'm going to do full screen and tell me if it's still okay. For whatever reason, Adobe doesn't allow full screen with slide sharing. Okay. What I will do, I can switch to a different reader, which is Preview. There are some animations later on, which is why I'm using Acrobat, but we can don't worry about that. Let me just stop the share. I'm going to switch to Preview, and we'll use that instead for now. Yeah. I'm just grabbing the file under Preview rather than Adobe. All right. Okay, now. Ooh.
There's it's rectangular here. It's
yep. How about now?
Perfect.
Okay, so yeah, Adobe doesn't like the screen. Yeah. Okay, so here's our set of objects: the dogs and the fish. Dogs from P, fish from Q, and our goal in this lecture is to find whether these distributions differ. Okay, and so this is the picture that we're having today. So yeah. All right. So I'm going to use the maximum mean discrepancy as my measure. So the maximum mean discrepancy can be interpreted in one of two ways. So one is as the difference of feature means. And this way should already be very intuitive to everyone, because yesterday we talked quite a lot about infinite dimensional feature vectors. So you might already have a sense of how we might be able to use these infinite dimensional feature vectors to find feature means to compare probabilities. The second way that we're going to look at is as something called an integral probability metric. And if you're not familiar with that, don't worry, because we're going to introduce it. But it turns out that for our purposes, the second way of understanding MMD is the better one. And for that, we're going to use our understanding of RKHSs as spaces of smooth functions. So the second notion of RKHS that we introduced yesterday. Then I will talk about statistical testing. So if I have a difference between distributions, I want to know, is it large, is it small? And statistical testing is a framework to think about whether a distance is large enough to be significant, so big enough that it's not likely to be due to chance. Right at the end, if we have some time, I might talk a little bit about training GANs using MMD. And that's, I think, a very interesting application area, because when you're using MMD to train GANs, you need to take quite a different approach to when you're using MMD to test. And we're going to see a little bit more about that later. OK, so let's first understand MMD in terms of a difference in feature means. So let's say that I have two Gaussians and they have different means, and I want to tell whether they're different Gaussians. So if you've done an elementary statistics course, you will have encountered the t-test, where you're going to compute the empirical means of these two Gaussians, and you'll see if they are different enough that it's unlikely to be due to chance. And if so, you're going to conclude that they're different. You'll reject the null, that they're the same. Now, what happens if we have two Gaussians with the same mean, but different variance? So evidently, like a t-test isn't the answer here, but you can look at features of these Gaussians. So the feature of the Gaussian which is relevant here is x squared. And if I compare the expectation of x squared for these two Gaussians, they're going to be different. Okay, so the density, which is the trace that I'm plotting here, these densities are chi-squared densities, and the two means are shown as bars, and you can see that the two means are different. And you could do a significance test to see if these means are far enough apart that it's unlikely to be due to chance when you compute them from samples. But then, somebody can give you a Gaussian and a Laplace distribution. And in this case, the feature that we defined on the previous slide isn't going to help us because I've drawn them to have the same variance. So, one could keep chasing features and say, well, I'm going to use the fourth moment, or I'll use another moment, and then someone will give me two distributions that match in that moment, and on and on. But, it seems that you need to guess in advance what the difference is going to be able to find the right feature. So what if we could use like infinitely many features? That might solve the problem. And lucky for us, we spent yesterday talking about how to use infinitely many features. So we're going to use kernel methods to attack this. So as a visual reminder from yesterday's slide, here's our notation. So let's say I've got a point x here. I define a feature of x, right? So this is my feature dictionary of x. It might have infinitely many entries. This notation here, if you recall, means that the features are square summable. So even though there's infinitely many of them, they're getting smaller and smaller as we go up our feature dictionary. A kernel is a dot product between the features. Okay, kxx prime is dot product of features of x and x prime. So even if we have an infinite feature dictionary, if our algorithm only uses dot products, we can manipulate these infinite feature dictionaries via their dot products. And if you'll remember from yesterday, the exponentiated quadratic kernel has this feature dictionary, which are these Hermite polynomials scaled by Gaussian envelopes, and getting sort of smaller and smaller as we go up the dictionary. Okay, so this was sort of yesterday's lecture in a slide. So this gives us a feature dictionary, but we want to compare probabilities. So what we could do is we could compare what I'm going to call the mean embeddings, which are the expected features of P. Okay, so EP of my feature, my ith feature, is the sort of the ith expected feature of my probability. And I've got this infinite vector of expected features. So once again, I'm able to use a kernel trick to deal with these infinite vectors of expected features. And in particular, the dot product of the expected feature of P and the expected feature of Q is the expectation under P and Q of my kernel between X drawn from P and Y drawn from Q. Okay, so I can manipulate my vectors of expected features as long as I only view them via their dot products with other expected features or with features of points. And I can do that using this expected kernel trick. Now, there is a little bit of fine print. The fine print is that if I take the expectation of my feature vector, the length of that expected feature vector has to still be finite. So if I take the sum of the squared entries of the expected features, that still has to be finite. If it isn't, then I'm going to have an infinite kernel, and that's boring. So yeah, as always, when I have infinitely long vectors, you have to be a little bit careful that you don't get tripped up. All right, so given that we are representing our probabilities by vectors of expected features, then what is a natural way to compare these vectors of expected features? Well, I can just take the difference between them. And if this difference is 0, then it seems likely that P and Q are the same. And we'll talk a little bit more about conditions for that, but let's for now just go with this. Okay, so I'm going to take the difference of expected features under P and Q, and I'll take the norm squared. Now remember that the norm squared of any Hilbert space element is the dot product of this with itself. Okay. Now we'll take the dot product of this with itself, and let's take the first term in this dot product, which is the dot product of mu p with itself. That's here. Second term, dot product of mu q with itself. That's here. And then twice the cross term, the dot product of mu p and mu q, which is the final term here. Okay. Now we're going to use the result from the previous slide to get a sum of 3 expected kernels. So expected kernel of k of x with itself, expected kernel of k of y with itself, expected kernel of x drawn from p with y drawn from q. This notation here is a little bit subtle. So what I mean by this is that x and x prime are 2 random variables, both with the distribution p. However, they need to be independent of each other. So remember, I've got the expected features of p, the expected features of p. These 2 expectations are independent. So when I have an expected kernel, these 2 variables have to remain independent of each other. Okay, so so I don't sort of get e of x squared is not the same as bracket e of x and then square. Okay, so now let's look how this appears when we return to our example from the beginning of the talk. So I have, let's say, 3 dogs drawn from P and 3 fish drawn from Q, and I want to compute the quantity from this slide using these objects. Okay, so using samples from P and samples from Q. I'm going to make a big table where each of the squares in this table is the kernel between one pair of objects. So how similar a given pair of objects are. So obviously my dog here is very similar to itself, and it's quite similar to this other dog, and it's a little less similar to this dog, but it's not at all similar to any of these fish. Okay, and I've got the same sort of structure among my fish. All right, so I compute the kernel between every pair of dogs, kernel between every pair of fish, kernel between my dog and my fish. And then this is my expression here. So average kernel between dog and dog, average kernel between fish and fish, minus twice the average kernel between dog and fish. And you'll notice here that I haven't allowed I and j to be the same. So when I say the average kernel between dog and dog, it's the average kernel between one dog and another dog, but I've excluded the similarity between a dog and itself. And that should remind you of this expression here, where I've taken x and x prime, which are independent, but from the same distribution. So how should I interpret this expression when I'm saying, is it the case that on average, the similarity between objects from the same distribution, dog to dog and fish to fish, is equal to the similarity between objects across distributions, so the similarity between dog and fish? Okay, so if on average dog to dog and fish to fish similarity are equal to dog to fish similarity, then it's likely that P and Q are from the same distribution. And if I see infinitely many dogs and fish, then that should approach 0 if the dog and fish distribution are the same. However, in this case, obviously dogs are much more similar to other dogs than they are to fish. So I'm going to get a big number here, and I'm going to conclude that the distributions are different. Okay, so this is the feature intuition for telling distributions apart. And this should be quite immediate from our lectures yesterday. We learned about dictionaries of infinitely many features, and now we're using these to compare distributions. However, there is another way to understand the distribution comparison that I've introduced, and I'm going to explain that now. Okay, so this is as an integral probability metric. So what does an integral probability metric mean? The idea of an integral probability metric is to capture the following intuition. If I show you these 2 sets of points, and without any statistical knowledge, I ask you, are they different? You're going to say, well, on the evidence that you've shown me, probably yes. And if I show you these 2 sets of points, and if I ask you, are these different? You'll say, well, from what you've shown me, I can't see a difference in these sets of points. Like maybe if you show me more points, there'll be a cluster of blue here and a cluster of red there. But right now, from the number of points you've shown me, it's hard to tell that these 2 sets of points are different in some sense. And so I want to capture this intuition that these sets of points are further apart than these sets of points. And integral probability metrics are a way of capturing that. So an integral probability metric is that I find a well-behaved function, in a sense that I'm not going to specify yet, which maximizes the difference in means under P and Q. So remember, x is drawn from P. I take the expectation under P of f of x. I take the expectation under Q of f of y. I take this difference in distributions, and I find a function which is well-behaved. which maximizes this difference in expectation. So it's very positive around my blue points, it's very negative around my red points. There's a minus sign up here, and so I'm going to get a large number. Now, this well-behavedness is essential because, in this case, well-behaved actually means smooth. And because my function is smooth, it can't go as positive around these blue points and as negative around these red points as it could here. So this function is telling me, or this class of functions, I should say, is telling me that these points are further apart than these points. And so, this is what an integral probability metric does. It says, like, find from a dictionary of smooth functions the function that maximizes the difference in expectations. And here I'm getting a difference which is larger than here. Okay, so what is my well-behaved function? Well, remember the notion from yesterday that RKHSs give us spaces of smooth functions. And so indeed, we're going to use the unit ball in a reproducing kernel Hilbert space as our class of well-behaved functions. And this tells me why I've called this the maximum mean discrepancy. I'm finding a function that maximizes the discrepancy in the means. So a function in a unit ball that pulls apart these means as far as possible. Now, remember from yesterday what a constraint like this does. The norm of F in the RKHS is a smoothness constraining norm from yesterday. And we force this norm of F to be less than or equal to 1. So this is our way of saying, I need my function to be smooth. So remember the final slide yesterday, where we're talking about why the RKHS norm is a smoothness enforcing norm. All right. And so, my functions here are going to be linear combinations of the features, where these feature dictionaries are exactly the feature dictionaries I was using earlier in this talk. So this will already be some foreshadowing for you. So my function of x, dot product of f and features of x, which are the sum of these infinitely many features. And this is a weighted sum where f1, f2, f3 are linear coefficients of the feature dictionaries that I used earlier in the talk. Okay. And what does this constraint mean? Well, the constraint, as you'll recall, means that the sum of the squared f's has to be less than or equal to 1. And this is going to ensure that I get a smooth function. All right. Now you can see that the Gauss versus Laplace example can be solved with this particular measure. Okay. So here's Gauss versus Laplace again, and you can see that the Laplace has more probability mass here in the center, and the Gauss has more probability mass here and here. And so you can see that the function goes negative where there's more blue, it goes positive where there's more red, and then when red and blue agree to be 0, the function goes flat. So this class of functions is able to detect Gauss versus Laplace. So it's able to solve that problem. So when is my function space rich enough that this is 0 only when P and Q agree? So what we would like is that we have a big enough function space that this thing basically is a metric on probabilities, which is to say that it's only 0 when P and Q are the same, and it's not 0 if there's any difference in P and Q. We're going to call reproducing kernel Hilbert spaces that have this property characteristic reproducing kernel Hilbert spaces. So these are the RKHSs that are rich enough that this is 0 when P and Q are the same. So for the purposes of this talk, I'm not going to derive I guess, properties of characteristic RKHS, so that would be a lecture on its own. I will tell you now that the exponentiated quadratic kernel that I've introduced earlier, that is characteristic. And I will also tell you a quick way of checking if a translation invariant kernel is characteristic, which is that you take its Fourier transform and check whether the Fourier transform is 0 on an interval. If it's not 0 on an interval, then it's characteristic. So easy way to check. Now, there's many other witness function classes that one could use, which are integral probability metrics. So one in particular, the class of functions of boundary variation 1 gives you the so-called Kolmogorov metrics. So in one dimension, that amounts to looking for the largest difference in cumulative distribution functions. The bounded Lipschitz functions give you the famous Wasserstein distances. So those are another very nice class of functions, which are very popular, for instance, in training GANs. And if we have a bit of time, we might revisit those later. So there's many different integral probability metrics besides the MMD. Okay, So I'm going to now link this notion of MMD, which is a smooth function that maximizes the difference in expectations, with the notion of MMD that I started the talk with, which is the difference of expected features under P and Q. So at first, it's not obvious at all why these things are the same. Like I've used the same expression for both, but right now, it's not clear why these are actually the same thing. Okay. So to show that they're the same thing, I'm going to use a property here, which I've put on the bottom of the slide, which is the expectation of an RKHS function of the random variable x, where x is drawn from P, is the dot product of the coefficients that define the function and the expected features. So in other words, I can sort of take the expectation. Remember, f of x is the dot product of f and features of x. I can take the expectation inside the dot product under the same condition that I used to take the expectation outside the kernel earlier in the talk. So when I said that the dot product of expected features was the expected kernel. All right, so now let's use this property in the next slide to show that our two notions of MMD are equal. Okay, so here's our second notion of MMD. I'm looking for a smooth function, a function in a unit ball that maximizes the difference in expectations under P and Q. Okay, so this is my function here. All right, now I'm going to use the trick from the previous slide. Expectation under P of F is the dot product of the expected features under P and the coefficients that define F. So here I've done that right here. I've done that for mu P, for EP of F, and mu Q for EQ of F. All right, now what is the function in the unit ball that maximizes this dot product? All right, so I'm going to show this graphically. Here is my unit ball. So F is living in this unit ball. And here is my mu P minus mu Q. So expected features of P and expected features of Q. So everything is in 2 dimensions here, but you have to believe that it's in infinite dimensions. So graphically speaking, what is the function that is going to maximize that dot product? So it's not going to be these functions, right? The function it's going to be is the function that aligns with that vector. In other words, F star, so the function that solves this optimization problem, is going to be the unit vector pointing in the direction of mu P minus mu Q. Now, if I take the dot product of a vector and a unit vector pointing in the same direction, what do I get? I just get the norm of the difference. I just get the norm of that vector, so norm of the difference of expected features under P and expected features under Q. And that's our first view of MMD. So the second view of MMD here is equivalent to the first view of the MMD. So looking for a smooth function that maximizes the difference in expectations is equivalent to looking at the norm of the difference of expected features. The function view is equivalent to the feature view. So are there questions at this point? No? Okay, good. All right. Now, earlier on, I plotted the witness function, which is the function that maximizes the difference in expectations. So where did those plots come from? How do I plot my witness function? Because isn't that a function of infinitely many features? So, how is it that I can plot this function of infinitely many features? So we're going to look at that now. Okay, so let's say that I have points drawn from P. Okay, x1 through xn drawn from P, and let's say that I have points drawn from Q, y1 through yn drawn from Q, and I want to plot the witness function for these two sets of points. Okay, so I'm going to first show you how I plot the witness function, and then I'm going to show you why that's the answer. Okay, so the how is the following. I take my kernel, in this case an exponentiated quadratic kernel, and I put a kernel on each of my blue points. I put a kernel on each of my red points. So blue bumps on blue points, red bumps on red points. I add all the blue bumps together to get a blue function. I add all the red bumps together to get a red function. I subtract red from blue. That's my witness up to some constant of proportionality. So even though it's a function of infinitely many features, conveniently for us, it's only in practice a function of the kernels evaluated at these points xi. So that's good because then even though it's an infinite feature function, I'm able to deal with it. Okay, why is that the answer? So remember from a couple of slides ago that f star, the function that maximizes the discrepancy in means, is up to a constant of proportionality, the expected features under P minus expected features under Q. All right. Now let's say that I've got samples from P. Okay, xi is samples from P. So mu p hat, which is the empirical feature mean, is just the mean of the features, okay, of the xi's. Now, if I want to plot my witness function at a point V, that's the dot product of the coefficients that define F and the features at V, which is, if I'm plotting it empirically, the difference in expected features under P minus expected features under Q with the features of V, dot producted with the features of V. Now, remember, okay, here's my empirical features of P up here. If I have this sum I equals 1 to m features of xi, and I take the dot product with the features of V, well, feature of xi dot producted with feature of V is just the kernel between xi and V. So I've got my sum of my kernels on xi minus the sum of the kernels on the yi. And that's my witness function up to some constant of proportionality. So, this is good news because, I can exploit the kernel trick. Because of the form of my witness function, I never need to worry about writing these infinite feature dictionaries. So it's an RKHS function, but it's a nice function, which allows me to take advantage of this kernel representation of the function. Okay, so that's my witness function. All right, so earlier when I gave talks about MMD, I would often be asked, well, MMD is a divergence between P and Q, but how does that relate to other divergence measures like KL or chi-squared? So the following little interlude is going to address that question. So let's zoom out. Broadly speaking, if I have P and I have Q and I want to tell them apart, what do I do? Okay, so there are sort of two concepts that I could use to attack this. One is that I could take their difference, okay, P minus Q. And if P minus Q is smaller, if it's 0, then P and Q are the same, okay? Or I could take a ratio, P on Q, in some sense, okay? And if this ratio is 1, then P and Q are the same. So these are two ideas that I could use to compare P and Q. So the first notion, the difference of distributions, this gives rise to the integral probability metrics. So if I'm trying to sort of witness my difference in distributions, one way that I could do it is by looking for a function whose difference in expectations, in effect witnesses my difference in distributions. So I find a function from some nice function class, and I take the difference in expectation of that function. And if for every single function in that class, the difference in expectations is 0, then I conclude P and Q are the same. But the sort of underlying property that I'm exploiting here is a difference, okay? Now the phi divergences are the ratio view, okay? So this phi function is a function of the ratio. So this function is going to be 0 when this ratio is 1, and it's going to be convex. And then I'm going to take the expectation of this function of the ratio. Well, this function is 0 when the ratio is 1. So this expectation is going to be 0 when P and Q agree. So the view from the phi divergences is a ratio view. The view from the integral probability metrics is a difference view. So in the integral probability metrics, we've got the MMD, as we've seen, we've got the Wasserstein distances, we've got the total variation distance, and so on. Okay. In this view, we've got the KL, we've got the Hellinger, we've got the chi-squared. Okay. So if this is a log, we're going to get a KL, or reverse KL actually. And so what you can see here is that these phi divergences are fundamentally different objects to the integral probability metrics. So you cannot write the KL as an integral probability metric, and you can't write the MMD as a phi divergence. Nonetheless, these two circles have a non-trivial overlap. Okay, so is this just a mistake in my slides, or is there really somebody who lives in between? And it turns out that there is a single measure of difference between probabilities that is both an IPM and a phi divergence, and that's the total variation distance. So the L1 distance between P and Q. And that's the only non-trivial divergence measure between distributions that is both an IPM and a phi divergence. No one else lives in that. At least no one non-trivial lives here. Okay, so this is the map that you should have in mind when you're thinking of different ways of comparing distributions. Like, do you want to use a ratio, in which case you're living on this side? Do you want to use a difference, in which case you're living on that side? And MMD is living on this side. All right, any questions about that?
There's one in the chat.
Mm-hmm.
You can read it if you like, or I can read it.
Maybe read it to me because I'm using full screen.
So phi divergences do not lead to Hilbertian structures. They are often non-symmetric. What you recommend as readings for the structure that phi divergence generate? Or what do you?
Yeah, so I think there is a nice paper by Igniting and Raftery called Proper Scoring Rules. So this is a very nice overview of, phi divergences and IPMs and other measures. So I would say that's a good paper. That's one that I found really helpful and interesting. Yeah.
Okay, maybe I have one question myself. Is that so the topologies induced by each metric, are they comparable? I mean, is there some results on the comparisons of the topologies?
Right. So this might be something we could, and I've got a further discussion of that later. But indeed, one has to be very careful. So, there is an ordering of the topologies, and KL, I think you can think of that as witnessing a strong topology, whereas an MMD or Wasserstein a weak topology. But yeah, that's certainly something that there is some slides where we're going to revisit that if we get to them. Otherwise, we can talk about later. Yeah. Okay.
Would you please say the paper title again?
Yes. So it's called Proper Scoring Rules, and it's by Igniting and Raftery. Yeah.
Okay. Thanks.
Yeah.
Another question?
Mm-hmm.
Yeah.
Go ahead.
Okay. Yeah. All right. So now let's talk about hypothesis testing. So we've got our MMD, and we're going to now use the MMD in a hypothesis test. So what do I mean when I'm saying hypothesis test? Well, let's say that I've computed my MMD, okay, which is average similarity of samples from P to P, average similarity of samples from Q to Q, minus average similarity of samples from P to Q. And a question I might ask now is, how does this help decide whether P and Q are from the same distribution? So, roughly speaking, if this quantity is big in quotes, then I might think that P and Q are different. If this quantity is small in quotes, I might conclude that P and Q are similar. But big and small are not, these are qualitative statements, not quantitative statements. So I might want to actually have something a little bit more specific than that. And in particular, I want a threshold below which I would conclude that, MMD is, it's sort of likely that P and Q are similar. So whereas if I exceed that threshold, if my MMD is greater than that threshold, then, this is unlikely under the hypothesis that P and Q are the same. So it's big enough that it's really unlikely that it arose just due to chance, despite P and Q being the same. Okay. So I now need some quantity which I would only exceed with low probability if P and Q were the same. Okay, so this is what I've written at the bottom of the slide. Let's say I want a false positive rate of alpha. So let's say that P and Q really are the same, and my MMD most of the time should be small. But with some very small probability, just by chance, it could be that I'm unlucky and my empirical MMD is large, even though P and Q really are the same. So I'm going to specify a false positive rate. I'm going to say, well, 95% of the time, if P and Q are the same, my empirical MMD should be smaller than some threshold. And then 5% of the time, I'm not going to be lucky. Okay, and I'll exceed that threshold. So the question now becomes, well, how do I actually compute this threshold? What do I do to obtain a threshold like that I can use to get a low false positive rate if P and Q are the same? All right. So to get a threshold like this, I need to explore a little bit the behavior of the maximum mean discrepancy when I'm computing it from samples. So, I've talked a lot about what MMD looks like when I've got infinitely many samples in the population setting. But now what happens when I'm computing it from samples? So to do this, I'm going to look at a little example here. Okay. So these sets of points here are drawn from 2D Laplace distributions, and you can see that the distributions are different. So red and blue are indeed from different distributions. I've drawn 200 points from P, 200 points from Q, and I've computed the squared MMD multiplied by the square root of number of samples for reasons I'm going to get to later. Okay, and from these 200 samples of P and Q, I've got an MMD of 1.2. All right, so what I'm going to do now is I'm going to construct a histogram where on the x-axis, I've got this square root of n times MMD squared, and on the y-axis, I've got the probability that I saw a particular square root of n times MMD squared. Now, so far, I've just computed it once, and I've seen only one value, which is 1.2. So I've put a bar here at 1.2. Let's repeat the experiment. So I've drawn 200 more samples from P and from Q, and I've got a new MMD. So it's not exactly the same because these samples are a little bit different, but it's close. It's 1.5. Okay, so now I've seen two MMDs. So I've put one bar at 1.2 here, and I've put another bar at 1.5 here. And this is my probability of seeing this quantity. So I've seen two values with equal probability. Let's repeat that experiment a few more times. So let's do it 150 times. And I've got this histogram here. Let's do it 300 times, 3,000 times. And as I'm doing this experiment more and more and more, what I'm noticing is that my MMDs are starting to resemble a particular distribution. And that distribution is the Gaussian distribution. So indeed, one can prove that in the limit, as one obtains more and more MMDs, the histogram of these MMDs is going to approach a Gaussian distribution. So as I sample, independent samples of P and Q, I compute my MMD, I repeat that experiment over and over and over and over and over, and I get the histogram of the MMDs. That's going to be Gaussian distributed around its mean. And it's going to have a variance Vn, which is going to drop as 1 on n. So basically, like as I get the mean of my MMDs, the variance is going to get smaller and smaller and smaller as I focus on my target. Okay, so this is why I multiplied by square root of n here, so that I could get something which is converging to an actual Gaussian. Okay, so this is the distribution that I expect of my MMDs under the assumption that P and Q are different. Okay, so it's Gaussian distributed around its mean. All right. So this is what I expect to see when P and Q are the same. But in fact, what I'm interested in, if we go back to our earlier question, is the threshold for MMD when P and Q are the same rather than different. Okay. So this is the behavior that I expect to see when P and Q are different. But what I'm interested in is the behavior of MMD when P and Q are the same. All right, so what happens when P and Q are the same? Okay, so let's say that I draw P and Q as standard Gaussians, okay? Now on the x-axis here, I'm going to plot not square root of n times MMD, but n times MMD, so that already should worry you a little bit. And on the y-axis, I'm going to plot the probability of seeing a particular n times MMD squared. Okay, so here I've done it 10 times. So I've got 10, items on my histogram, and this is what I've seen so far. One thing you'll notice is that I'm seeing MMDs that are less than 0. Should this surprise you? Well, hopefully not. The reason is because let's go back to our statistic. If we look at our statistic here, we've got the average P to P similarity plus average Q to Q similarity minus average P to Q similarity. But I'm computing this from samples. So even if P and Q are the same, it might just be by chance that these first two numbers are a little bit smaller than twice this number. And so I'm going to get a number which is negative. Another way to understand this is that this quantity here is an unbiased empirical estimate of a quantity whose mean is 0. So because it's unbiased, I should expect to see a few positive numbers, a few negative numbers. All right. So this is why I'm seeing a few of these empirical MMDs less than 0, a few of them above 0, but the mean is going to be 0. Okay, let's get 20, 50, 100, 1000. Now, unfortunately, this is not looking like a Gaussian. Okay, and indeed, it's not a Gaussian. So the asymptotic distribution of the maximum mean discrepancy when P and Q are different is actually an infinite weighted sum of chi-squareds. And this is multiplying by n here rather than square root of n. So basically, like as my number of samples increases, I need to, the variance of my MMD when P and Q are the same actually drops a lot faster than it does when P and Q are different. So remember, when P and Q are different, the variance is dropping as 1 on n. Okay, so as I see more and more samples, my Gaussian is squeezing down with variance dropping as 1 on n. When P and Q are the same, the variance is squeezing down a lot faster as 1 on n squared. So that's a little bit different. Okay, where do these weights of this infinite weighted sum of chi-squared come from? They come from the eigenvalues of my kernel with respect to my P, my distribution with which I draw my x's. Okay, and it's a centered kernel, which is just I'm centering in feature space, but don't worry about that. Okay, so this is what this distribution looks like. And as you might suppose, the distribution here is actually very, very difficult to compute. So in the event that P is Gaussian and my kernel is Gaussian, I have closed form expressions for these lambdas and I can compute this distribution. But most of the time, I don't actually know P. I've only got samples from P. And my kernel might not be Gaussian. And so in practice, these weights here can be extremely hard to compute. And this is a little bit of a problem because I want a threshold for this distribution. Like I want a quantile of this distribution such that I exceed this quantile, this threshold, with low probability when P and Q are the same. But it seems incredibly tough to compute quantiles of a distribution which is an infinite weighted sum of chi-squareds. So we're going to return to this problem. But for now, let's just look at a little summary of what we found so far. Okay, so in the event that P and Q are the same, the distribution is an infinite weighted sum of chi-squareds. In the event that P and Q are different, I get a Gaussian distribution. Okay, and I'm multiplying by n here. The correct scaling when P and Q are different is square root of n. So this is why this Gaussian is sort of very blurry, because I'm scaling it by a number which is sort of bigger than it should be scaled by, given its asymptotic behavior. And then this curve here is the behavior I expect to see when P and Q are the same. And graphically, this is what I want to do with my test. Okay, so this is how I expect the statistic to behave, the MMD to behave when P and Q are the same. And I want a 1 minus alpha quantile of that distribution, right? I want a threshold such that I will only exceed that threshold with probability alpha, where alpha is something small, when P and Q are the same. And this is going to define my test. I'm going to say, like, I'm going to have a small number of false positives when P and Q are the same. Now, what happens when P and Q are different? Okay, when P and Q are not the same, this blue curve shows me the expected behavior of my MMD when P and Q are not the same. Okay, and what I would like is a small number of false negatives. All right, so I would like, ideally that when P and Q are not the same, the probability of going below this threshold should be something small. And as I see more and more samples, what's going to happen is that my MMD scaled by n is going to go to infinity, and this variance is going to blow up, and this area is going to go to 0. So that's going to be a nice property. Are there questions about this? Yep. No questions. Okay, good.
I have a quick question, Nader.
You have a question. Okay, what is your question?
About this, so I'm curious, what is the role of the kernel in the asymptotic distribution of the MMD?
Right, no, that's a good question. So let's go back. The kernel does very much influence the shape of the distribution, right? So let's first consider the case when P and Q are the same. The lambdas here, which scale my infinite weighted sum of chi-squareds, are indeed functions of this kernel, because these are the eigenfunctions of the kernel with respect to P. So as I'm changing my kernel, I'm going to expect to see these lambdas change, and I'm going to expect to see different eigenfunctions. Okay.
No, okay. You didn't finish. No, sorry.
Yeah. So I mean, one could even do like a thought experiment. Like imagine that I've got a Gaussian kernel and I make it really, really, really wide. Okay. If I make this Gaussian kernel very, very wide, then all of the terms in my MMD sum are going to become equal because basically my kernel is going to become a constant function. And if my kernel is going to be a constant function and all my kernels are equal, then my MMD is going to concentrate down to a spike at 0, right?
Right.
So you can sort of see that the distribution here is then going to be very, very concentrated at 0. So this infinite weighted sum is going to concentrate down to 0. So just intuitively, you can see that the choice of kernel is going to affect the distribution that you get here.
So at the end, it would also affect the threshold that you would get.
Indeed, right? So that's exactly right. So the shape of this distribution is going to change. And consequently, the quantile of that distribution, so the 95th quantile, is going to move. It's going to move around as I change my kernel. And not only is the choice of kernel going to shift around my distribution when P and Q are the same, but also it's going to change what's going to happen when P and Q are different. So when P and Q are different, my asymptotic distribution is always Gaussian. So I always expect my MMDs to be Gaussian distributed around their mean. And the variance is always going to collapse like this. So as I see more and more samples as I compute my MMD with more and more samples, the MMD is always going to collapse towards its mean at speed 1 on n, or yeah. However, this variance here is a function of the kernel. Okay, so it's going to drop as 1 on n, but the constant in front of that 1 on n is going to depend on the kernel that I choose. So if I choose particular kernel, it might be bigger or smaller, even though it's always going to drop as 1 on n, and even though the shape is always going to be a Gaussian shape.
I see.
Yep.
Thank you.
There are two more questions.
Yep.
So maybe one that is a bit maybe related to the notation regarding the unbiasedness of the estimator. Would somebody suggest? Actually, Jonas suggests. Would you perhaps rewrite the estimate as MMD square and then you put the hat on the top of it to show that it's an unbiased estimate of the positive population quantity?
Right. So would I? Yeah, I mean, it could be that it's that could be a better way to do it. I guess my LaTeX looked really ugly when I put a square. When I put the head over the square. So yeah, basically you should think of this as an unbiased estimate of the square MMD.
Okay.
That's the best way to think of it. But that's basically because LaTeX looks horrible if you put the square underneath. What you should just understand it as, though, is this expression here. And from this definition, we know that we have an unbiased estimate. Yeah.
All right. And the other question, maybe it's a bit tricky to answer shortly, is the behavior of the distribution of the estimator when P is different from Q. What is the behavior, let's say, when P gets closer to Q? Is it like smoothly converging to a chi-squared, or?
Yeah, so no, that's actually an interesting question. So indeed, as P and Q approach, the distribution, you can even do like a numerical experiment. The distribution does get closer to this weighted sum of chi-squareds. And so in a sense, for small numbers of samples, if P and Q are very, very close and you compute the asymptotic distribution, it is going to somehow look a little bit like the null rather than the alternative. Even though as n increases, eventually you're going to see it converging to the Gaussian. This interpolation between null and alternative is something that I think Kenji Fukumitsu has used in some of his work. So that's, I mean, again, it's sort of out of scope for this lecture. But if you get in touch with me later on the message boards, I can address that and give some more information about that.
All right, I think that's all.
Yep. Cool. So yeah, so these are good questions. Okay, so as I've said, this threshold is a real pain to compute, right? Except in some very special cases, it will be very hard to get this in closed form. And so a question then becomes, well, you know, I'm a practitioner. I've got an MMD. I've computed it from my data. I want a threshold. What do I do? And an answer to that question, I'm going to illustrate graphically. So let's say, you know, back to our dogs and fish example, I've got a collection of dogs, I've got a collection of fish, and I want to compute, I've computed the MOD between my dogs and my fish. And now I want a threshold, like, is this number big, is it small? Okay. So visually, here is my kernel matrices, matrix, where I've got on the top left here, my kernel between my pairs of dogs, on the bottom right, my kernel between my pairs of fish, and then the off-diagonal blocks are my kernels between my dogs and my fish. And I can see my dogs are more similar to other dogs than they are to fish. All right. So now I want a threshold. So what I could do is I could take all my dogs, all my fish, put them in a bag, draw half of the contents of that bag and call them X tilde, right? And half the contents of that bag and call them Y tilde. So I'm going to call these mer dogs. So it's like half dog, half fish. Okay. So X tilde is a set of like half dog, half fish, and Y tilde are a set of half dog, half fish. And now let's compute the kernels between my X tildes, my kernels between my Y tildes, and my kernel between X tilde and Y tilde. And what you can see here is that the structure that we had earlier is now no longer visible. Okay, because like, you know, if I have X tilde, which is like half of them are dogs, half of them are fish, and I take the kernel between them, and here X tilde and Y tilde, both X tilde and Y tilde are half dog, half fish. I compute the kernels between them. If I take the average of the top left block plus the average of the bottom right block, and I subtract from it the average of these off-diagonal blocks, then this is going to be a small number. And it's going to be simulating from the case that P and Q are the same. All right. And so now imagine, you know, I'm going to do this many, many times. Okay, so I basically like re-scramble my dogs and fish. I compute these kernel matrices. I compute the MMD. I re-scramble my dogs and fish, compute the matrices, compute MMD. I repeat that over and over and over. If P and Q are the same, then the histogram that I get is going to simulate this red curve here. And you can prove it. So you can prove that if I do this permutation and I get the histogram of my points, that as I permute more and more and compute the histogram more and more finely, and as I see more and more samples from my P and my Q, I'm going to end up getting this histogram here. And if I then take the threshold, that will be the correct threshold to get the right false positive rate when P and Q are the same. What happens when P and Q are different? Well, then I'm going to get a threshold for the mixture of P and Q, right? So I'm going to get a threshold from a simulated null distribution, which is half P, half Q. And that's fine because this threshold will be fixed. But as I see more and more samples, the true MMD scaled by n is going to go off to infinity, which means the probability of false negatives is going to go down to 0. And I'm going to get the right behavior when P and Q are different. So when P and Q are the same, I'll get the right false positive rate. When P and Q are different, I'll get a false negative rate that goes to 0 as I see more samples. And so this permutation approach is going to give me a correct test. Are there questions about that?
I think I don't see any question in the chat.
Okay.
Anybody wants to say something? I think no. Oh, yeah, I think you can go ahead.
Okay, cool. So now the next question is, how do I choose the best kernel? And so this goes back to some of the issues raised by Critic earlier, which is that all of the things in this curve depend on my kernel, right? And I want to choose the best kernel. What does that even mean? Okay. So a test power depends on many things. It depends on, so, you know, the power is the probability of a false negative, just to be clear. So it depends on the kernel. It depends on P, it depends on Q, it depends on how many samples I've seen. Now, I have specified earlier that if my kernel is characteristic, then my population MMD is not going to be 0 if P and Q are different. Okay, so that means that, as we've seen earlier, the power, the probability of false negatives, goes to 1 as I see more samples. So as I see more samples, I'm not going to mistakenly think that P and Q are the same. However, it may be that for the n that I've seen, so the number of data that the world has given me, I might still end up having very poor power if I choose a bad kernel, even if the kernel is characteristic. Okay, so the limit of infinite data is a very distant limit in some cases. So even if I have a characteristic kernel, I might need massive amounts of data before I notice that P and Q is different to 0. It is different to 0, but in practice, it might be more data than the world has given me. Okay, so in the space of characteristic kernels, I might want to choose a good kernel for my problem. All right, and a good kernel for a problem, which is an n-dependent, like this will depend on n, is something that I can choose in a problem-specific way. So there isn't a single characteristic kernel that solves all problems best, right? Different problems are going to use different characteristic kernels to get good power for finite n. Okay, so there's not a one kernel fits all. Okay, so let's first of all consider the case of the exponentiated quadratic kernel. We know it's characteristic, but we do have a choice to make, and the choice is how broad my kernel is going to be. Is it going to be a narrow kernel? Is it going to be a wide kernel? Okay, for any sigma in the infinite sample limit, my MMD is not going to be 0. But for finite samples, choosing a good kernel might give me a more or less powerful test. Okay, so choice of sigma is very important for finite n. And visually, you can see that. Okay, so let's look at this little toy problem here. Okay, I'm trying to get an MMD, which is going to tell red from blue. And here is my witness function. So the function that I computed earlier when I'm computing my IPM, which is positive on my blue and negative on my red. Okay, and I'm computing this for a particular sigma. Now, what happens if I use a much broader sigma? Well, this function is getting closer and closer to flat. Okay, so my MMD is going to be closer and closer to 0. And it seems that this function is not very good at telling my red from my blue. So wherever I arrange my red from my blue, this function is going to be flat, and it's not going to tell me very much. What if I choose too narrow a kernel? Well, my MMD here is going to be large, okay? But what you're seeing is that my witness function is sort of spiking around every sample that I see. So it's true that my MMD is going to be large for this example, but it's going to be large however I arrange my points. And so, basically, whatever arrangement of my blue and red points I get, I'm going to get a big MMD. And so it's going to be hard to distinguish the MMD when blue and red are genuinely from different distributions to the MMD I get when blue and red are from the same distribution, because I'm going to get a large MMD whatever I do. So basically, this is about right. This is too broad. This is too narrow. And I want basically to find a way to choose the right kernel among all of these options. Okay. There's even a more subtle point, which is that maybe the exponentiated quadratic kernel isn't a good kernel for my problem. So if X and Y are images, I might need to train some feature extractors from those images before I can do a test. Okay, so maybe I want to train a deep neural net, which is going to extract features from my images to be used in a statistical test. And I need a way to do that. Okay, so how do I choose the best kernel, right? I've given an intuition, but now let's make this a little bit mathematical. So remember, this is the distribution of my MMD under the assumption that P and Q are the same. I've got a threshold here, okay, which is the 1 minus alpha quantile. So 95% of the time I fall below that threshold, 5% of the time I'm going to be above it. And here is the, in blue, the behavior I expect of the MMD when P and Q are different. And here is the proportion of false negatives. So alpha is a design parameter of my test. So as a user, I'm going to say that 95% of the time, I want my MMD to be below that threshold when P and Q are the same. Okay. And so given that false positive rate, the best kernel is going to minimize my false negative rate. So it's going to say, well, if P and Q are different, I want to minimize the fraction of the time that I mistakenly say that P and Q are the same. Now, remember, as I was telling Critic earlier, every single item on these plots is a function of the kernel that I've chosen. Okay, so this quantile here, that's a function of the kernel. This blue curve here, its mean and variance, is a function of the kernel, as well as P and Q. So as I'm changing my kernel, like let's say I've got an exponentiated quadratic kernel and I'm changing its bandwidth, all of these things are going to be moving around. And I want to, somehow optimize over my kernel bandwidth to minimize this area. Now, this seems a very tough problem, okay? Because everything is moving, like this quantile is moving. This quantile is, the 1 minus alpha quantile of an infinite weighted sum of chi-squareds, which I approximated using a permutation procedure. It seems that I've given myself a very tough problem if I want to minimize this blue area. But that's what I have to do. Like, this is my goal if I want to choose like the best kernel from my class of kernels for my problem at hand. All right, so how do I solve this very difficult problem? Let's write in mathematics the expression for this area here. So the probability, this subscript 1 means under the alternative, which is to say under the P not equal to Q setting. I want the probability that n times my squared MMD is greater than this threshold, this C alpha threshold, which is the 1 minus alpha quantile under the null, under the assumption that P and Q are the same. Okay, so the distribution under the alternative of my test statistic multiplied by n exceeding that threshold. So what's interesting is that the probability distribution under the alternative, as you'll recall, has a simple Gaussian form. Okay, so that means that I can write this probability as the CDF of the standard Gaussian of this quantity here minus this quantity here. So what I've done first of all is that the probability of n times MMD exceeding this threshold is the probability of MMD exceeding this threshold divided by n. So that's where the C alpha divided by n comes from. And then I've used the asymptotic form of my MMD distribution under the alternative, which is a Gaussian with population mean MMD squared and variance Vn. Okay, and remember the variance Vn is dropping as 1 on n. So as I see more samples, my variance is going to drop and my MMD is going to concentrate down onto its mean. All right, so I need to basically maximize the probability here. Okay, so I want to basically say when P and Q are different, I want the largest possible probability of exceeding a threshold. I want to maximize this quantity. Now, this is a little bit troublesome because of this term here. So the C alpha is a function of my kernel, and it's going to give me some grief. However, remember that my variance is dropping as 1 on n. So square root of variance is dropping as root n. 1 divided by square root of variance is growing as root n. Okay, so this term here, this first term, is going to grow as root n. This second term here is going to shrink as root n, because I'm multiplying in the denominator by n. So if I've seen a reasonable number of samples, then this first term is going to be much bigger than this second term. So to a good approximation, I'm able to neglect this term here when I'm trying to choose the kernel that maximizes my test power, so maximizes the probability of being large. And that makes sense because under the null, the null distribution's variance is dropping as square root of n. It's dropping as n squared. And so basically, like for large enough samples, that threshold, isn't all that important, right? Because what's important is just pushing my MMD large and dropping its variance under the alternative. So for large enough n, the second term is negligible. And to maximize test power, what I need to do is effectively just maximize the signal to noise. So maximize the ratio of the MMD to its variance. Okay. Graphically, what does that look like? It looks like pushing this blue curve to the right and making the variance of this blue curve as small as I can. If I push the blue curve to the right and make its variance small, then this area here is going to be shrunk. Okay, so this is the signal to noise notion. Are there any questions about that?
one question from an earlier slide. Patrick is asking, yeah, interesting. Why do we need to put P equal Q as the null hypothesis and not P different from Q? And he argues that for training a GAN or GMMN, then my default assumption will be that it's sampling from different distribution. And he adds, this will also make the calculating threshold easier because it's from an approximately normal distribution.
Right. So, I mean, in the present setting, our goal is a particular case, which is to test that P and Q are the same. So, you know, one needs to think of the applications that one has in mind. So as one example, like, you know, let's say that, you know, you have a machine that you're running and you're taking measurements of, like, you know, vibration levels of that machine. What you might care about is, like, is the machine malfunctioning? So I've taken a set of readings on day 1, I've taken a set of readings on day 2. Are they from the same distribution? And it may be that if I take a set of readings on day 1 and take a set of readings on day 20, day 20, the machine breaks and the set of readings that I take are from a different distribution, and that should alert me. So the question that I'm trying to answer here are these two distributions different? You know, another example, like I'm in medicine, I'm taking blood pressure medication. I take a set of blood pressure readings on day 1, set of blood pressure readings on day 2. Are they from the same distribution? Hopefully, yes, because my blood pressure is within some reasonable limits. But if on day 20, I get a different distribution of readings, then it may be that I've fallen very ill. So this is the question that I'm asking here. Like the question is if P and Q are from the same distribution. And to answer that question, I need a threshold which I will exceed when things go wrong. So when P and Q are no longer from the same distribution. So indeed, for this setting, I need to solve this harder question, which is to find a quantile of my distribution when P and Q are the same. Because, you know, what I'm trying to test here is, you know, the issue of when P and Q become from different distributions. Now, indeed, you know, when P and Q are from different distributions, the asymptotic behavior of my statistic is much simpler. It's a Gaussian. And, you know, if I can work in that setting, then finding thresholds will be simpler. So I can give an example of such a setting, which is like, let's say that I have a reference set of samples R. Okay, so let's put myself in the GAN setting. Let's say I have GAN number 1 and GAN number 2. And GAN 1 is making its pitches of bedrooms, and GAN 2 is making its pitches of bedrooms. And I want to know which of my GANs is better. Okay. So I have a set of samples from my first GAN, a set of samples from my second GAN. And I also have a set of real bedrooms, okay? So I've got my set of real bedrooms, I've got my GAN 1 samples, I've got my GAN 2 samples. Neither of my GANs are making perfect bedrooms, okay? Because it's, you know, drawing perfect bedrooms is a harder problem than a GAN can solve. However, it might be that one of my GANs is drawing its set of bedrooms closer to the real ones than my second GAN. So let's say that GAN 1 is a little bit better. In this case, I've got 2 MMDs. I've got MMD between GAN 1 and my real set of bedrooms. I've got MMD between GAN 2 and my real set of bedrooms. And I want to know if MMD 1 is significantly smaller than MMD 2. In this case, MMD 1 is Gaussian, MMD 2 is Gaussian, and I can do a hypothesis test of whether MMD 1 is significantly smaller than MMD 2. In this case, exactly as you say, the statistical question becomes much easier because my MMD1 and MMD2 are both Gaussian distributed. So that is a setting where I can take advantage of the simpler asymptotic distribution of my MMD when the null isn't true for either of my samples.
Perfect. So that's all.
Yep. Okay. Yeah, but you know, sadly, in the setting I'm describing, or sadly, I mean, it happens in the setting I'm describing here, that the goal is to tell whether P and Q are the same or not. And there are lots of practical settings where that is a legitimate and correct goal. And P and Q, like the null hypothesis, isn't a vacuous hypothesis. Like that is a reasonable hypothesis to have. Okay, so let's say that I'm choosing my kernel to maximize the test power. It's important not to choose the kernel on the same data set that you're testing, because if you do that, you're going to get way too many false positives. Okay, so let's say I've got data from P and data from Q. I'm going to split it into red and orange. Okay, so half of my data is going to be my red, half of my data is going to be my orange, and I'm going to do the same for my samples of Q. I'm going to split into red and orange. I'm going to use my red data to choose my kernel Q, choose my kernel K, which is going to be the kernel that maximizes this ratio here. And then I'm going to use my orange data for testing. So once I've chosen my kernel, I use that chosen kernel, which I've learned on my red data, to test on my orange data. And that means that I'm not going to get the wrong number of false positives. Whereas if I chose my kernel on the same data I was testing, you're going to very quickly see you're going to get way too many false positives. All right. So I'm going to now describe a case where I'm learning kernels on deep features of my data. In this example here, my deep features of my data are going to be just, a very relatively shallow, I think 3-layer fully connected net with quadratic nonlinearities. So these are neural nets parameterized by theta. Okay. And then my overall kernel is going to be 1 minus epsilon of my Gaussian kernel on my deep features plus epsilon times a Gaussian kernel, multiplying this overall thing. So this is a little bit of a sort of heuristic thing that I've sort of got a combination of a Gaussian kernel on deep features and a Gaussian kernel overall. This is just something that we found was helpful to get good tests out. So this is an engineering solution. Nonetheless, this kernel is characteristic because I've got this epsilon times a characteristic kernel. So ultimately, this kernel will always be able to tell the difference between samples of P and Q. On this plot here, what I'm showing is red and blue samples and the contours of this kernel K theta. And you'll see that unlike a Gaussian kernel, the shape of the kernel is changing as I move around my space. So on the left-hand side of the plot, the kernel is tilted basically diagonally to the left. And on the right-hand side of the plot, the kernel is tilted diagonally to the right. And you can sort of see visually why that is, because basically the blue sets of points are just blobs, but the red set of points are, basically tilted blobs, where the blobs are sort of tilted to the left on this side and tilted to the right on that side. And so the shape of the kernel, which is able to tell red from blue, is going to change as I move around my space. In the middle, the kernel is sort of spherical because there the red and the blue blobs have more or less the same distribution. Okay, so the sort of take home from this little 2D example is that even in 2 dimensions, it can help to have a kernel that's changing shape around the space if the goal is to tell red from blue with high test power. Okay, so this is a little toy example, but what happens if I go into high dimensional spaces? So what happens when X and Y are images and my deep networks are something like convolutional neural nets? So here's an example, which is the example that I started my whole course with, which is the CFAR 10 versus CFAR 10.1. Okay, so CFAR 10.1 is a distribution over little images, which the authors tried to make as close as possible to the original CFAR 10. But nonetheless, the space of images that CFAR 10.1 is drawn from has shifted over time. Okay, so the data set, I think they got their data from Flickr, and over 10 years, the distribution of Flickr images has changed over time in very subtle ways. And so I can use my MMD test to tell that there exists a significant difference between the images drawn from CFAR 10 and the images drawn from CFAR 10.1. So I'm going to reject the null if I do this experiment 75% of the time. If I'm testing CFAR 10 against CFAR 10.1. But if I test CFAR 10 against another CFAR 10 set, then I'm going to reject the null only 5% of the time because they're samples drawn from the same distribution. So this problem, if I'm just using an exponentiated quadratic kernel on my images, of course, I'm going to get the null. It's not a powerful enough kernel for the number of samples that I've seen to tell apart CFAR 10 and CFAR 10.1. I would need vastly more samples, impractically more samples. However, if I use deep features, which I train to maximize my test power using the criterion that I just described, then I'm able to tell apart C510 and C510.1. So this is a paper that we've just had accepted to ICML 2020. So you can have a look at that. And we've linked in the paper to some code so you can try it out. Okay, are there questions about that?
So I have a question.
Mm-hmm.
So here, the kernels, maybe this is related also to your first lecture. So how should I think about the RKHS associated with these kernels?
Right. Yeah, so this is a sort of interesting case, right? Because as my sort of initial step, I'm passing my images through a convolutional neural net, which gives me like a set of features, and then I'm computing features of those features, right? So remember that my exponentiated quadratic kernel then takes the input features from the convnet and computes infinitely many features of those features.
Mm-hmm.
So think of my RKHS as giving me smooth functions of my convolutional features of my data. And I'm using those smooth functions to tell apart my samples.
Mm-hmm.
But it's extremely important to use those convolutional features because, taking smooth functions of, in pixel space isn't very helpful. I need to first of all find features of my images and then take smooth functions of those features if I want to do a test of whether, C510 and C510.1 are different. So it's sort of a hybrid of kernels and convnets to solve this problem.
I also had a question about this epsilon.
Yep.
So I think I had a look at the paper once, and I thought that this epsilon is somehow there to like guarantee that even if your network training goes completely aboard, you still have some guarantees, right? But you said initially that we know already that with this Q kernel, you're not going to do anything. So you're kind of like trying to keep a guarantee that in practice won't help at all. So I'm a bit like, I don't really see why this, I mean, I see why it's beneficial from a theoretical viewpoint, but let's say in all applications that you will have, I feel like you propose something that you think is better, but you still want to keep the old guarantee. Or is there any deep reason to do this?
Yeah, so basically, I would say there's a theoretical reason, which I think is a little bit sort of for our own, shall we say, self-delusion, and there's a practical reason. So the theoretical reason is that indeed, because I've added epsilon times Q, my kernel remains characteristic because this Q is a characteristic kernel. And this is sort of true, but it's also not interesting for images. There's also, and this is something actually, if you look at the little video that we've prepared for ICML, a somewhat practical reason, which is that these k-on features of the data, this can behave a little bit oddly as I move my x far from the support of most of my points, and so this Q here basically like crushes that weird behavior, and means that the kernel, it sort of causes us to have a better behaved kernel. Which ends up being very important in practice when we're using it in a test, so as not to get a vacuous test. So I will say that this construction of the kernel here is like an engineering solution to get a family of kernels that is good for the problem that we're doing.
Okay.
But nonetheless, what's I think important is that using this family of kernels and optimizing by maximizing test power, we get a good problem. We get a good kernel for the problem of telling apart these distributions of images, in the sense that it has good power when the distributions are from different, when P and Q are different distributions, while having the right false positive rate. So when I take my samples both from P, I get a 5% false positive rate, as I should do. Yeah. So in a sense, like I've hypothesized a kernel which is good for this class of problems. I've optimized the parameters by maximizing test power, and I've verified that it does indeed solve the problem that I wanted to solve. So it's an engineering solution which has been the right solution for this setting.
Okay, yeah, thanks.
So Maximilian is asking one extra question. What objective were the convnets trained on to get features that are useful for kernel methods?
Yep, so the objective is exactly this objective here, right? Maximize test power. That's what we trained on. Yep, because that is our loss function for this setting. Like we have two sets of objects. We want to find the most powerful tests to pull them apart. And this is the criterion that you should optimize if that's your goal.
Okay. Yeah, I guess we should move on because but there's no extra question. There's 10 minutes remaining.
Yep. So I'm only, as I think I had supposed at the start of the talk, I will talk very briefly about GANs. But this is just to give a little flavor of that area. So I'm not going to get through all the GAN slides, but I will just give some discussions. Okay. So one thing you might do with an MMD is to use it as a critic, right? So I have a measure of distance between two sets of objects, and in a GAN, I have a generator generating a set of objects, and I want to use my critic to compare that with a set of reference objects. Well, MMD compares two sets of objects, so it seems a natural candidate for that problem. Okay, just as a quick visual reminder, and this is actually visual notation that I'll be using in my slides. My generator, which I'm going to show as a little naive artist here, is going to generate some images. I'm going to take that set of images, and I'm going to compare it to a set of reference images. My critic is going to get feedback to my students, and this is going to cycle until I reach some stationary point where either my student stops improving or my critic can no longer tell my real from my fake dogs. Okay, so this is my sort of visual GAN. All right. And in the universe, there are many possible critic functions. I can use Wasserstein, I can use MMD, I can use Hellinger KL chi-squared. So there are many possible critic functions I might use as my teacher here to tell my real from my fake dogs. All right. What I'm not going to cover is the generator. I'm going to just assume I've got a generator, which is my little student, which takes noise and makes dogs. But if you want to read about generators, there's other papers you can read about. So all I care about for this talk is the critic. Now, briefly, it would appear that an F-divergence, which is divergence living on this side of my plot, is an unhelpful critic. Now, what do I mean by an unhelpful critic? Here is the Jensen-Shannon divergence, which is the divergence which motivated the original GAN paper. And let's say that my P and my Q, my two distributions, are with disjoint support. So my P is supported on this interval here, and my Q is supported on that interval there. And the support is disjoint. Okay. Now, let's say that my red is the distribution of samples that my student is producing, and the blue is the reference. Okay. Let's say now that my student has improved. Okay, my student started here, and now my student's getting closer to the target. Unfortunately, the Jensen-Shannon hasn't changed at all. Okay, here it's log 2, there it's log 2. And that seems a little bit unfortunate because my student's getting closer to my target, but my teacher is just like not telling me that I've got any closer. So my visual cue for that is this angry teacher here that whatever you do, just yells no. Okay, so unless you're perfect, the teacher is just going to yell, no, you're wrong, you're wrong, you're wrong, whatever you do. And this is an unhelpful critic, right? Because if the teacher just keeps yelling, you're wrong, whatever you do, then you're not going to be able to improve what you're doing. Okay, and so superficially, it seems that Jensen-Shannon is not going to be a good critic for GANs, and yet Jensen-Shannon is one of the most popular critics that is used. So evidently, like something's going on. What's going on is that you're not actually computing Jensen-Shannon, you're computing a variational approximation to the Jensen-Shannon, which is a little bit more helpful. Okay. And one other thing that you might do is to add something called instance noise. So if I take my red and I blur it by adding noise, then it will have some overlap. And so my Jensen-Shannon will be more helpful. Okay. And this instant noise is equivalent approximately to a data-dependent gradient penalty on the variational approximation. So basically, Jensen-Shannon, if you were doing it perfectly, would not be a helpful critic. And to the extent that GANs work, it's because they're not computing Jensen-Shannon, but they're computing a lower bound on it, which ends up being useful for GANs. Okay, so that's all I'm going to say about F-divergences for this talk. If you're interested in more, then there's my NeurIPS tutorial, or on my webpage, I've got slides of a talk I gave at Oxford where I go into this in much more detail. But I won't talk about that more. I'm going to now talk about integral probability metrics. So interval probability metrics are helpful critic witnesses. So here is, for example, the Wasserstein distance. So this is looking for functions of Lipschitz norm bounded by 1 that maximize difference in expectations. So this is a different class of well-behaved functions to the MMD. This class of well-behaved functions is the class of functions with this Lipschitz norm here bounded by 1. Okay. Now here is Wasserstein when I've got my samples red and blue here. And you can see that it's getting smaller as my red approaches my blue. So this is a helpful teacher. As my red approaches my blue, my Wasserstein distance is getting smaller. And I'm telling my student, yeah, you're getting better. You're improving. Like, keep going in the direction you're going, and you're going to get a nice answer. All right. And to understand a little bit more about Wasserstein distances, I've provided some references at the bottom of the slide, so you can understand a little bit more formally what behavior is going on here. Okay, how about MMD? So MMD for the kernel that I've used for this slide is a helpful critic. Okay, so as I move my red to my blue, MMD is going, oops, from 1.8 down to 1.1. So my teacher is telling me that I'm getting closer. Is MMD always a helpful critic? Well, maybe not. So here I've computed MMD with a much narrower kernel. And as I move my red to my blue, MMD is, well, you know, it's dropping a tiny, tiny amount. But it's not dropping very much. Okay. And so it seems here that this is one of these bad teachers that just yells at you that you're wrong, whatever you do, unless you get the answer right. So it seems that unlike Wasserstein for MMD, whether your teacher is a helpful teacher or a teacher that just yells at you is going to depend on whether you chose a good kernel or not. Okay, so how do you choose a good kernel? We need to use, in this case, a regularization strategy. Okay, so using MMD to tell apart as a gradient critic, like this is a very old idea. It was proposed back in 2015. But even for MNIST, you're not getting great digits from that. Okay, so these original papers were just computing MMD, you know, using either pre-baked features or using Gaussian kernels direct on the images. This is not going to give you great images. You need better image features. In particular, just as we did in testing, we need to learn convolutional features of our images before computing the MMD on top of those. We can either use the linear kernel on those convolutional features, and so that's within this Wasserstein-GAN framework, or we can use a nonlinear kernel on those features, and that's within this framework here. So we're going to stick to this side, but what I'm going to talk about also applies to the other side as well. All right. So let's just see in a small number of dimensions, if I'm using convolutional features, or if I'm using deep features of my data, this is going to change the shape of the kernels on those features. So here I'm computing kernels directly on my data. Here is my witness function. If I compute kernels on deep features of my data, then my kernel is going to change shape in different parts of my space. Okay. So here I'm getting a narrow kernel. Here I'm getting a broader kernel. And I'm getting this function, which is going to actually adapt to my space in complicated ways. Okay. And I want to give a useful gradient to my generator. Now, earlier on, I talked about training kernels on deep features of my data to maximize test power. Is that a good idea here? No, it is not, right? Because like choosing a kernel which gives me really good test power means that I have a witness function that's very confident that my real and my fake samples are far away from each other. But that doesn't mean that I'm going to give a good signal to my student, right? My MMD is going to be really large. It's going to be absolutely confident that red and blue are different. However, you know, this is my angry teacher that just yells no, because I'm going to be very confident that my red and my blue samples are different. But I'm not going to be able to provide a useful signal to my student to move its red points closer to the blue points. So actually, to choose good critic features for an MMD, I need to weaken my function class. I need to make it less good so that I give a useful signal to my student to make it get closer to my teacher. So this is kind of funny. Like originally, when we tried to train MMDs, we tried to train MMDs to maximize the power. and the GAN just wasn't training. And then we figured out, actually, we have to do the opposite thing for testing. We have to make a weaker critic to maximize test power. Since I'm out of time, I'm not going to talk much about that. I'll just talk very briefly about how I weaken my critic. So I weaken my critic by scaling MMD by a sort of penalty quantity. And that penalty quantity tells me, at a very high level, that I want my features, my feature gradients not to change much as I move around my real points. So in other words, as I move around my real points, I want my function to be flat. And as I move away from my real points, my function is allowed to be less smooth. And so this gives a sort of adaptive penalty to my MMD, which ensures that it's going to give a useful signal to my student. All right. I should also emphasize, like, when you're training GANs, a kitchen sink approach helps. So we are using this gradient penalty, but you should also use other forms of regularization. Like, you should basically throw all of them in, and then you're going to get good performance. So the spectral norm regularizer is a regularizer that's complementary to the gradient penalty regularizer. You can also use an entropic regularizer, which avoids mode collapse. So basically, like, many different regularizers together are helpful when you're going to get good images. And just to end the talk, here are the images that we got with MMD GAN using this regularization approach on ImageNet, like unconditional ImageNet. So this is interesting because we haven't tried to do a class conditional GAN. We've just said, like, draw me some pictures of the world, and train the GAN on all of ImageNet without labels. And at least when we did this paper, we were getting state of the art. Probably now state of the art has moved on. But nonetheless, here is our fuzzy images. So I think now is a good time to stop for questions. So I will stop for questions.
So I think we are a bit tight for extra questions because there's a meeting right after, but there is a roundtable in half an hour.
Sure.
So,
okay. So I will answer questions when the roundtable.
Yeah, I guess that's fine, right? So Thanks a lot, Arthur, for this lecture. I think this is really great. It's really an example of how really explaining, like, kernel methods in depth, even for beginners, and with a lot of insights. So I'm sure there will be lots of questions in the roundtable in half an hour. So see you.
Yep, I will see you then.
Bye.
Thank you. So after this lecture, there is a virtual booth with Bloomberg. So come join to the next session that we will start soon.
And I will also say, check my post-credit scene. This is like when Thanos comes and says that he's going to get the Infinity Stone. So that's this paper, just for reference.
All right. Bye-bye.
Thanks a lot.
Bye.